So continue. So today it's a pleasure to have Marco Lorenzi from Inria. So Marco actually did his PhD in the same place that I did, and afterwards a quick postdoc in London. He became a tenured research scientist at Inria, Sophia, Antipolis, Université Côte. So his research interests in the development of statistical and machine learning methods for the analysis of large-scale and heterogeneous biomedical data, with current topics being Bayesian modeling, uncertainty quantification, time series analysis, latent variable models, and federated learning. And it's a really pleasure to have you here, Marco. Yeah, floor is yours.
Thanks, Ender. And again, thank you very much for your invitation to present to your meeting. I think it's very nice, and I like very much what you're putting in place there with this series of talks. I think it's a very nice initiative. So yeah, today what I would like to present you is some relatively new research path that we are exploring here in this in our lab that I'm trying to develop with some students, which is related to federated learning. And this is not, let's say, it's quite a new concept, and especially in the medical imaging community, although it's booming, right? So, but we came actually, we got to this because very practical exigencies. So the point is that we need a data set, and if you're not lucky enough to be in a hospital or like being in an institute where you have facilities and access to cohorts, studies, and data, well, data access is a big concern. So what is the paradigm? If you want to gather together enough samples for doing your research, you need to, well, ask people to either access their dataset or send you the data. And this has been, let's say, the working paradigm since forever. But it's becoming more and more complicated because you need to gather more and more, like a larger and larger data set, simply because the methods that we are now using are really data hungry. And also there are many regulations, and especially we have related to privacy and data protection. So it's becoming extremely difficult to simply gather the data set together. And can you see the slides?
I am seeing the presenter view, like the next slide and your notes and so on.
Oh, you're seeing this one?
No, I'm seeing the normal slides. So it's a bit odd.
Oh, interesting. Okay.
I also see the presenter view. So
you also see the presenter view.
Okay. Yes. Let me. What if? So you see the presenter view still?
Mm-hmm.
Yeah.
Let me see. I try to. Maybe what I can do, I can remove this. Tell me if now it is better.
Yeah, now it works.
Okay, I had the two screens, so I removed one. Okay, so yeah, so what to do for if you want actually to address this problem is well, start collaborating and developing methods that are compatible with this secured paradigm. And that's where actually federated learning well, found its own way into the research world. And the paradigm of federated learning is quite simple. So we have several entities, centers, clients, hospitals. Here I'm showing, well, I took this figure from a recent papers on federated learning in healthcare. So we can imagine having different hospitals, each hospital its own data set. Hospitals are willing to participate in a research project. They cannot actually share their data. They cannot let their data go outside their own server. So we can have a centralized entity. So we have this sort of star-shaped architecture. And what the centers can do, they can actually train or do some work locally. So train some model, estimate some parameters. And what they can share is not the data itself, but is the parameters. So we can aggregate together the parameters, centralize them, and then we can do some mathematical operations, some statistical approach to simply aggregate them to estimate some sort of meta model that is supposed actually to represent appropriately the variability of these different centers. So we can have this federated model, and then we can iterate this process. We can send back this federated model to all the hospitals that they can use this, for example, as initialization for another iteration steps. And we can iterate this over and over. So everything, all this concept of federated learning is about sharing parameters and not data and aggregating them and finding the proper rules to put together parameters and guaranteeing that we are doing the proper things, so that at the end, all this iterative aggregation and re-estimation process leads to something which is meaningful, that makes sense. So the concept is powerful because it solves the problem of data protection. Data is not disclosed, although it doesn't solve completely the problem of privacy, because parameters can still actually leak some information from the data that has been used to train them, but this is another issue. But already this paradigm is compliant and can solve, is very powerful actually for many applications. And healthcare is one of these applications because data is very sensitive. So you might have witnessed, you might know about the explosion actually of federated learning. Everyone these days talks about federated learning. And you can see here, I made a very quick, simple query on PubMed, on paper published in federated learning. You can see that 2017, when the word federated learning was proposed in the seminal work of McMahon. So in the matter of 2-3 years now, there's an explosion of papers more and more, especially in healthcare. So there is already several reviews of the state of the art, several papers actually proposing some sort of federated learning approach for some healthcare application or some kind of healthcare data set. So this is becoming one of the state-of-the-art paradigm for machine learning in collaborative setting. And yeah, already in our own research, it was 2016, and we were actually thinking already in this sort of federated learning, but without calling it federated learning because we didn't even know we could call it like that, because the term has been introduced later. But we were already dealing with this problem because we have collaborative initiatives. For example, Enigma, which is this large consortium of hospitals that they share data for imaging genetic studies. So there was this problem of multivariate studies with the brain imaging and genetic features. And so, like, how to deploy a multivariate analysis model in centers that cannot share their data. And we came with this simple approach. So for example, we can do partial least square, which is simply, the basic operation of partial least square, estimating a covariance matrix between these different kind of features that I denote here X and Y. It could be genetic and imaging for different subjects. And we have to estimate an SVD. So it's basically a sort of PCA for cross-modality data. And so we have to estimate eigenvalues and eigenvectors. And let's imagine that the data, so our data matrix is partitioned across centers. So we have all the data, the features of genetic for the center 1, and then center 2 up to center M, and same for the imaging. So it's very simple to see that computing this covariance matrix is basically, well, the product center-wise of, so it's the sum center-wise of the covariance matrices for each center. This is just a simple matrix multiplication, so simple algebra. And so this is interesting because it means that to estimate a large covariance matrix between different centers, we can just sum the covariance matrices of each single center. So we could ask to each center just its own covariance matrix without disclosing their data. Or even simpler, we can just ask every center to estimate some eigenmodes and just send us those eigenvectors and eigenvalues. And then we can plug them together, and we obtain an estimate of the covariance matrix. And actually this works, this is quite effective. So, and this was a way at the time to do some sort of federated learning for this kind of application, so sort of linear models of variability. So this was 2016. Then things evolved, especially the same year, actually the year after, McMahon from Google came with this approach, which is called federated averaging, which was proposed for training neural networks. So here we're talking about way more complex model, so non-convex problems also. And the idea was very simple. Federated averaging, as the word says, relies on, well, we have this sort of function that we want to optimize. So we have some local loss function at each center that depends on the parameter that at the end we wish to federate or to estimate in a collaborative manner. So we can imagine that we want to optimize this function, which is a weighted sum of the cost of the functional at each center. And the weights are, well, could be arbitrary. Let's say that classically weights are assumed to be the contribution in terms of data points of each center to the problem. And so what do we do? Well, basically we just estimate, so yeah, in a more general form, what we can replace this weighting just by PC, which is just the importance that the server gives to every center in this weighted average, in this weighted sum. And so every center can actually, in the federated averaging, sense estimates is a parameter by running, for example, E epochs through SGD, and transmits the parameter to the server, and the server performs aggregation in the form of, well, an averaging where the weights depends on, indeed, on this coefficient, the PC, so on the local on the importance of each center, for example, in terms of data points. And so basically, we can decouple this sum, so this weighting aggregation. We can imagine we can even subsample a set of centers, so we can actually ask only few participants to perform the operation, so the update. So receiving updated parameters for certain centers participating, we can aggregate this parameter, and for the one who do not participate, we simply replace their contribution with the previous estimate of the model, so the global one. And once we perform this aggregation, we obtain a new estimate of the parameters at the server level. So we can send all this estimate back to the clients that will use it for a new SGD optimization. So a series of SGD steps starting from this initialization. And this is how federated averaging works. So it's very simple. We just assume that all the weights of our neural networks are ID, and we just well, weight so we estimate them independently through just weighted averages. Why this makes sense? As simple as it is, it makes sense because there's been quite a lot of research in the last couple of years proving that under certain conditions, especially condition of smoothness of the loss function, so what we call Lipschitz H smoothness, and some condition on the bound of the, well, on the unbiased gradient that we can estimate through SGD at the client level. So it means that if we can take batches and we compute the expectation under the batches of the local gradient, we get actually an estimate of the gradient of the client. And under the assumption that these estimations are bounded, so we get close to the original client in expectation up to certain parameters, sigma square. So these are all conditions, assumption on the fact that the problem we are solving, we are working with functions which are well behaved, with estimation that we are well behaved. But based on these assumptions, it can be proven that we have this actually process of aggregation converges with a certain bounds, and the bounds, well, depending on which kind of assumption we take and how we develop things, different kind of bounds can be found, but most of them are very similar, and they are just they are scaled by the number of total communication round. So it means that the more we go on with this back and forth of estimation and averaging, and well, the closer actually we get to convergence. And then there are some modulation. It depends on the smoothness of the functions and on the bound of the variance and so on. But these are all very similar.
Marco,
yeah.
What is sub I and what is sub C?
Oh, C is a center.
Mm-hmm.
So here this aggregation of the weighted norm of the gradient. And actually, yes, I apologize. I is the same of C. Still a center.
Okay.
Yeah, it was my bad actually when I brought down the equations. Yeah. So yeah, it just means that at the center level, we can do SGD, so we can estimate stochastically the loss function and its own gradient. And this is, well, getting close in expectations when we accumulate them to the original gradient. And this last inequality just tells us that this aggregation process of the gradients is bounded somehow with this bound that we can have here. So these are actually standard, the world of federated averaging inherits a lot from the world of distributed optimization. So all of these actually requirements here are the typical requirement that we have in distributed optimization. And indeed, the problem is a distributed optimization problem with some other, let's say, constraint, because, well, it's this federated aspect. We have this, well, also this fact that the data cannot leak, we cannot move it, and so on. But it's a sort of as a spin-off of that research world. So federated averaging makes sense. These are results that you can see that are taken from this seminal paper of McMahon that show that indeed when we move on through the communication rounds, things are, well, converge with different speed of convergence depending on how many, well, batches and epochs we use at every client. So the longer the epochs, the more difficult things are to converge, because it means that every client has the time to optimize a lot locally, so it gets very different. So we are averaging things which are more dissimilar, and so we will take longer actually to converge. Well, if we don't allow clients to go too far, then when we aggregate, things are moving, let's say, more coherently, although globally we might take a lot to converge to something which is specific to the client itself. The Achilles heel of this kind of approaches of federated learning is heterogeneity. Because in heterogeneity already, again, this paper, when we increase, so we partition MNIST, for example, to clients that share different kinds of digits, its client, and so on. So things, like convergence is much slower. And sometimes, yeah, people struggle actually to get convergence. And the heterogeneities can be due to a different number of problems. And I found that this very nice description of the heterogeneity is a recent paper, still in archive of Kairos, is a position, well, is a review from most of the prominent people in federated learning. And they're just saying, let's assume that we have this joint distribution of features and labels, and we index with I for every client. So depending on how we decompose, we factorize this joint distribution, we can identify different kind of heterogeneity. So this could be to covariate shift, so the features that vary, even though the probability of the label given the features is the same. So for example, we have the same word, but different writing styles. So every client is a person with his own different way of characterizing the features. Then we can have the condition of the features given the label that could be different. So this is a style change. So same object, a car, but different backgrounds. For example, snow, or like I don't know, in the countryside and so on. And then a very classical problem, which is the problem of label distribution. So labels that are site dependent. So certain sites might not even have some labels. So overall, the marginal of the label is different across the clients. And then even the label condition in the features might be different. So reviews, even if you have the same features, the same film, but for different people, the film can be good or could be bad. So all of this generates different kind of heterogeneity that have to be handled. And of course, when we average things together, models that have been trained in each of the different clients, depending on each this different sort of variability of non-iidness, things can go very bad. Actually, we can get models that do not make sense or are not representative of anything. And the other problem, which is also a byproduct of heterogeneity, but is also a problem general of federated learning, is that, well, this can be extremely slow before converging. And also as a technical issue, federated averaging in this paradigm that I mentioned, we are always bound to the slowest client. We have always to wait someone. So if we have some certain centers, clients, which are very slow in communicating, in sending back their updates, we are just stuck. And also, if we sample them, and we can say, okay, let's sample only some of them, but what I showed before, this sort of aggregation with sampling, in this, if you sample uniformly across the client's distribution, we have a bias. So what we have at the end, we don't guarantee that we represent everyone as they should. So depending on this weight that I mentioned before. So many issues. That's why people are doing a lot of research on this. And so there have been different ways of addressing the problem of heterogeneity or optimality of the aggregations. So one very notable approach, which is one of the state-of-the-art approaches, FedProx. So we change the problem of the client side. We make it a regularized optimization problem. So we introduce this proximal term where we just bound the optimization at the clients of the parameters in such a way they do not diverge too much from the initialization. So every client is forced, so we prevent clients to overfit their own data, but always be somehow in the neighborhood of the global parameters. But here we have a problem, we have to tune this, and in a federated manner it's extremely difficult because we don't have access to the local data, so we don't know exactly what's happening over there. And if you have to imagine designing this experiment involving hospitals, and you have to tune this parameter on the fly, this can be extremely complicated. And it's very slow again, because the convergence is even slower in this case. Then there are a lot of approaches that have been proposed recently, and I see more and more that they come with a machine learning solution, like making some assumption about the availability of some shared data or public data, or of the client that they can synthesize some data or share part of their data, or we can use all this model distillation, meta learning, multitask, and so on to find actually this joint model that accounts for all the differences. So this is a quite active field of research. The problem, so some of these approaches, they violate even the key assumption that, they assume that there is some data that can leak from the client to the server to do some sort of tuning of the parameters, or we move the problem from one side to the other, because then we need to be ensured that what we are synthesizing or sharing or distillating makes sense, and this is actually not guaranteed. And again, most of the time these things are so complicated that it's impossible even to imagine how we can prove that this is unbiased, makes sense, or converges. And then there's this last kind of approaches, which is, well, sampling, but finding different way of sampling. Sampling in a way that things are unbiased. So it means that we can find some statistical way, or like some sampling approach to select peak clients ensuring that in expectation, repeating the sampling over and over, we are going to converge to the original actually weighting. This is something that in the vanilla version of federated averaging is not guaranteed. And trying to find in sampling approaches that deal with this problem of heterogeneity. So favoring sampling of things to improve actually representativity of the clients. And the basic idea comes from, again, the paper of FedProx, which is another approach that they propose in that work, which is, let's assume, so for example, in this case, we have 5 clients, and 5 clients with their own weights, with their own way, for example, the number of data points. So we can imagine this to be probabilities attached to a multinomial distribution. So that give us the probability of sampling a specific client based on this sort of histogram. So we can sample with replacement. So at the end, the stochastic weight you can imagine is just over the m samples that we pick. So the m client that we would like to select among all the many. We just, for that client, we assign 1 every time we pick the client among the m tries. And then, so this is with the same replacement. So it means that we can pick the client more than once in the same iteration. And some client might not be picked at all because well, it's just the sampling in this distribution. And so you can see that this formula actually guarantees the unbiasedness because on average, well, every client will be represented with this sampling with replacement based on his original probability in the distribution of the clients. And so this is actually providing an unbiased sampling strategy, which is good. It comes, however, with some drawback, because it means that now something that before in federated averaging, we just gather all the clients together is a deterministic operation. Now it becomes a stochastic operation. So we have some variance that we introduce. So this is a random variable. And so it's for every client, we have this sort of Bernoulli tries. So each client is associated with his own probability P. And so we have a variance for each client in his selection process, in his way. So the weights vary, and so they can generate actually through the iteration variability in the way we converge, because in the way we aggregate, we have variability in the model we produce. And also we have a probability of a client to be selected, which is, well, in this case, with multinomial distribution takes this form. And again, so it means that certain clients have more probability of being selected than others. But there's no way to control them for representativity in this case, because we all are based on this original P that we designed at the beginning. So the question is, these are the statistical characterization of the sampling scheme, which is the multinomial distribution. Is there a way to do better than this? For example, decreasing the variance, finding a different way of sampling things in order to have a decreased variance, and perhaps a better representativity of the client based on some characteristic we would like to enhance. And this is actually what we proposed, what we addressed in a recent paper with Jan Fraboni, which is a student working here with me. And so the idea was what we call cluster sampling. So the idea is that instead of sampling according to this multimodal distribution M clients, so with the replacement, we instead define M different distribution, and we select the clients based each time on one of these distributions. So we sample M times, but every time we change basically the base distribution from which we sample. So we can have different weightings of the client for every sample. So it's a sort of extension, it's a special, so it's a more general case of what I showed you before on this cluster sample, on the multinomial distribution, right? So it means that for every round of samples, of sampling, the probability of sampling a client is just indexed by the distribution K. So we have a sort of matrix. So we sample these K clients, and every time we have to pick the client according to its own probability. So over the n client, we have different probabilities. So we have a varying probability, and every times we pick, we change basically the underlying probability among which we pick the clients. So this is the scheme that we defined. So it's a generalization. Why we wanted to do this? Well, I will show you later why this actually makes sense. The first thing is that why this makes sense? Does this make sense? And what does it mean actually defining this set of distributions? Well, there is a theorem that can be proven. So there are two sufficient conditions. If we can design this matrix of coefficient R, ik, okay, I, such that they sum on the rows to 1, so they define the valid probability density function, and they sum on the columns according to this formula. So this is M, so the total number of clients that we sample, times pi, so the original probability that the weight that we attach at the beginning to the client. So if actually these conditions are satisfied, then it's guaranteed that this sampling scheme, so sampling scheme according to the distribution here, is unbiased. So it satisfies our original requirement. So in expectation, we obtain the same of doing weighted averaging of all the clients together. And why this is nice? Because actually it can be proven that the variance of this kind of scheme is bounded by the variance of the original scheme based on the multinomial distribution. So it means that we can actually have a lower variance sampling, so decrease actually the uncertainty along the optimization. And the representativity of the client, so the probability of a client being selected at that round, ST is the set of clients which are selected at that optimization round in federated learning. So it's actually bounded below by the original scheme of multinomial distribution. So we can improve the representativity of the clients with this sampling scheme.
So I don't think I understood the last part. So is that probability, is that marginalized over all these iterations?
No, for the given iterations. So the probability of the client ending up in the set of clients that have been selected for then performing the aggregation at that moment of at that round of federated learning is actually greater or equal than the probability of the client being selected if we were sampling with a multinomial distribution. This for a given round.
Then I didn't understand. Why do you take the product over K?
OK is so we are sampling K times from K equal
at every
to 1
iteration, you sample K times.
Yeah. So
OK. For every gradient step, you actually do K sampling.
Yeah.
With different probability distributions. OK.
So what happens is that we are running a federated optimization round. So we ask all the clients to do their local optimization, but then we pick only M of them. How do we pick them? We either select them, so sample them according to this multinomial distribution. But actually what we do, we first select them and then we ask them to do the work so that we don't keep all the clients busy all the time. So either we sample K of them or M of them according to the multinomial distribution and we say, okay, now you do the work and you send me back the parameters that I do the aggregation. Or what we are proposing here, we pick M of them, but we pick them according to this different distribution. So the first one we selected by sampling from this distribution. The second one we selecting sampling from this distribution, and so on. So basically we have this, so we multiply over K the probabilities of not being. So if you want overall, if it's selected in this round, so if it's among the M, well, we have to accumulate, we have to multiply the probability of not being selected by any in any of the distribution, which is basically this one. And this is a bound on the original. So we have the potential. This is not saying that we do better. We always have better variance or more representativity because we have the equal here. But with this scheme, so we can actually improve. So in MD distribution, multinomial distribution, we have basically only one row here because we always use the same row, the same probabilities. It's just replicating the same row over the different K. While here we use a different weighting of the row for every peak, every time we pick it. So there are some nice theoretical guarantees or some promise theoretical that we can do better if you use the scheme over the standard approach of federated learning. And there is also a theorem that tells us that if you use the scheme, we converge. And the bound is very similar to the one of federated learning. So it means that the scheme makes sense, even though we are changing the way we select things, but we still converge asymptotically with the number of rounds of iterations. And why we call it cluster sampling? Because basically we can imagine each distribution to be a sort of define a cluster. So define clients which have high probability of being picked together from clients which are not. And every time we select a different distribution, we basically we pick clients from a certain cluster. So the problem is that how do we define the cluster? And this is our chance to define way of sampling clients in a meaningful way. For example, to enhance the representativity of clients that have certain features respect to others, or to put together clients which are similar. So we will give high probability in a given distribution to clients which are similar. And then when we switch to the next distribution, we try to sample other clients which are similar according to the same criterion. So different clusters. So basically we have to reimagine this to be different cluster, and we are allowed to pick one representative for every cluster to get our M representative to aggregate together. That's basically the idea. Okay, and that's why we call it cluster sampling. But more generally, it's just we have n different distribution, and every time we select it, we pick from one of these distributions. And so how to find the best sampling or clustering strategy. So basically, we would like to optimize this matrix of coefficients to optimize some criterion. And this is very difficult. There is not a general rule. It's a very post problem depending on which criterion we use. And for example, if we want to find a clustering that minimizes the variance, this is an NP-hard problem. So it's not something we wanted to deal with. So why not actually just defining some heuristics to define these clusters, these distributions, and prove that the heuristics actually it provides a valid rule for having this sampling. So, and the rule is that the rows have to sum to 1 and the columns have to sum to MPI. So, because you know this is a sufficient condition. So any sort of choice here that respects actually these two constraints, it's a good one. We know that we are doing things properly. So one idea is, okay, let's sample clients based on how much they are represented. So how many data points they have. So we would like to put all the clients that have a lot of points in separated clusters, so distribution, and put all the clients that have less data points together in their own cluster. Why not? So I give you a numerical example to give you so just a simple example to give you the idea. So for example, here we have 5 clients, 20 data points overall between all the clients, and we want to sample 3 of them only. So we want to define this 3 distribution from which to sample the first one, the second one, and the third one. And let's just say that this is actually the number of data points owned by each of the clients. So we have 5, 7, 2, 4, and 2 for the 5 clients. So the idea is that, okay, let's multiply everything by k, so by the number of clients we want to sample. So these are the numbers. And basically, it's like we have items, and we need to place all these items in the 3 buckets, knowing that each bucket can contain 20 objects at max. Well, this intuitive things to do is we start from the largest one, and we fill the first bucket with all the elements of the largest client. So it's 21, so we fill one bucket completely, and the second one only one element. And then we move to the next one, so 15 item, we fill it, and then we move to the next one, and so on. So at the end, we fill all the buckets because we have k times n, so this is an integer divider of number of clusters and number of elements. So we know that we can always do this. And for the same reason, we know that this satisfies our properties because, well, this sums to 1 on the rows, and on the columns we have the overall number of elements, which is indeed k times this original number of samples. And what you see, what's happening here is that we define a cluster in which the largest client is always selected. So this will be always represented. And then we have other clusters in which the other clients will be selected according to their relative representativity. So this is a way that is compatible with our cluster sampling to actually define sampling distributions, which are different from the multinomial distribution one, and respect actually, so what we said. So this is the first principle. And yeah, here you have the algorithm. It's just basically integer division just to assign and take the reminder, and then we iterate that and we keep assigning to buckets until we process all the elements of a given client, and then we move to the next. And we know that this algorithm, so if we apply this procedure, we satisfy actually our conditions for our cluster sampling. So this is a valid sampling strategy. There could be more refined ones, which are more interesting. For example, based on client similarity, we can define similarity between clients in any possible ways. For example, we can compute the similarity between updates. So what the clients are going to send us is their updated parameters. So we can check, for example, the cosine distance between sets of parameters. So we can define this sort of similarity matrix between all the clients, so all their updates. And we can apply on the similarity matrix any sort of clustering approach, for example, hierarchical clustering. And we can cut actually the hierarchical clustering at any level to define a partitioning of the data. So the idea is that now we can think about what we did before with the elements of the clients, but now actually we don't have clients with their own number of data points, but we have partitions with their own number of data points. And we can apply a very similar trick. So we can fill in buckets depending on the cluster that we are defining with this clustering algorithm. So we will start putting in the first bucket all the clients which are represented in the largest of these clusters, and then we can move to the next one and so on. So what are we doing in that case? We are defining probability that favor like groups of clients which are very similar. So we increase actually the probability of pick clients at this given selection which are very similar between them. And then when we move to the next, we move to a next kind of cluster, so a next similarity. So we somehow intuitively, we increase the representativity of different kind of clients. Okay.
Marco, can I,
Yeah.
I have a question.
Sure.
So if a certain client is not selected, then that client does not update their weights for that iteration?
Well, that client, it will receive then the update, the global update at the next round, and will start from that update. Every client,
Okay.
when the client is involved from the federated learning, is starting from the updates that you receive from the server, and it updates on that.
Okay. And okay, thank you. And I have one more question that is, I think, a more basic one. So just comparing federated averaging, where you're not sampling, you're just asking everyone to update their weights, and then you're taking a weighted average of the weights, and then sampling from a multinomial distribution, which is the base method for what you showed. So what is the advantage? I think you mentioned this, but I missed it somehow. What is the advantage of sampling as compared to federated average?
That we reduce the computational load, so the work required to the clients. Not all the clients are involved, so we minimize the chances, for example, to have stragglers. So clients that are very slow, we are not going to ask them all the time to do some work.
I see.
Because of this sampling procedure.
But on average, you will ask them that many times to do the work because it's not biased.
Exactly.
So actually, the computational load doesn't really change.
This is actually what, in expectation, we know that they will be represented over the sampling procedure. As soon as we sample, as long as we sample, they will be represented with their own proper weights. But on that given iteration, they might not be required. So actually, over the potentially hundreds of clients, we might sample only tens of them. So things are speed up. That's the idea of, that's why we want an unbiased sampling scheme, because we know that in expectation, we are doing things exactly as they should be in the original averaging, but we gain that we don't require work from everyone.
No, it's not biased. On expectation, you get the same average. But if you sample, doesn't that mean that you get as many samples in the end? So yeah, anyway, doesn't matter.
Yeah, well, it's statistical in expectations. It means that then we will iterate again. Every round we sample again, but across all the rounds, things will be represented with their own original probability. So that's the idea.
So at the end of the day, federated averaging is like the benchmark performance.
Exactly.
Okay.
Exactly. Very slow, but this is what this unbiased scheme they use is the reference sampling scheme, the reference scheme for average. Okay, so the essence of this work is just defining different way of sampling things to improve some quality. For example, reduce the heterogeneity between the different the way we sample things. So this is the idea of this cluster sampling based on similarity what I'm showing here. So it makes sense. We can also prove that if you do things this way, we obtain a matrix of R, Ki, of coefficients, which is compatible with our sufficient condition. So this is a valid sampling scheme, and it has all the nice properties. So it converges, and potentially it minimizes variance. And here I give you this example, which is quite, I think, hopefully clarifying. So we took MNIST. We define 100 clients, and we define 10 clusters of clients. Each of these 10 clusters so has 10 clients, and each cluster has one digit only. And so there is a clear heterogeneity depending on the label. And at every iteration, we sample 10 clients. So ideally, to the optimal way, and which is what we call target, is that at every iteration we sample one and only one clients representative of its own cluster, so of its own digits, right? And so you can see, so target, this ideal strategy is the orange one. And then we have MD sampling, which is the blue one, and the two algorithms that I showed. So this is based on the representativity, the green one, and the red one is based on this similarity. So the most important plot is this one, in which you see that, well, target, this is per round, how many clients of each class is selected. And of course, target by definition, every time samples one client per class. So we have 10 clients all the time, which are selected. So 10 classes which are correctly picked every round. You can see that MD And even algorithm 1 actually are suboptimal. So it means that they are never or rarely, they sample actually one representative per class. But many times we have overlapping classes just because, well, that's a multinomial distribution. So, and each of them now has 1/10 probability of being picked. And, well, 100 if we give them the same weight.
So this plus tells us that after some iterations, let's say 50, the algorithm 2 samples each client
exactly
once in the iterations. Okay.
Yeah. So what it's telling us is that when we give it, let's say, enough time to have proper models at each client, it's very easy to identify models which are trained on the same data sets, or they have similar data sets, not the same, it's similar data sets. So it's simple, it's easy to cluster them together. And this is what we are seeing here. At some point, the clusters are so well defined that we can define perfectly the 10 different buckets that assign one probability to each of the cluster, so that every time we just pick clients from that cluster. And to confirm a bit also the other properties we see that the convergence actually to the accuracy and the loss of this sampling based on similarity, well, is much improved, and the variability is generally very low. Because we avoid actually all this, well, it's a demonstration also of our bounds that we identify the origin. So if you have the proper sampling scheme, indeed the variance and the representativity is improved. So this is an empirical demonstration of these two theoretical results that we showed before.
Can I ask another question here?
Yeah.
So I'm a bit confused now because in the previous set of questions, you said that the main advantage here is you don't sample each client every time. So basically you have a computational advantage. But now it looks like algorithm 2 samples each client at every iteration.
Not each client, but each class, which is what we want. We don't sample.
I thought each client was actually, each number was in one class, one client.
In one class. So there are 100 clients.
Ah, okay.
And 10 classes, so 10 clusters of clients.
I see, okay. Thank you.
Of 10 clients each. So these are the classes which are sampled, correct? So that are the unique classes which are sampled at every iteration.
I see, okay, thanks.
I have another question here. So like at the moment, this is for MNIST?
This is MNIST, yeah.
Which is relatively easy dataset. And we see already it takes some time to identify these clusters. Do you think this will scale like to larger images?
Yeah. Yeah, that's a good question. So we have another, this is CIFAR. And we generated synthetically heterogeneity. So we sampled the clients based on Dirichlet distribution, where there's this alpha parameters that defines the heterogeneity between the different samples. So the different partitioning of the data sets. So for example, you can see a data set with 100 clients, and these are the classes distribution that we sample when we set alpha equal to 10. And here is the same, but when alpha is much lower, 0.001. So you see that the heterogeneity between clients of the classes which are represented is much higher. And this is CIFAR, so it's a more complex benchmark than MNIST. And but the figures somehow is similar. So what we show is that when there is no heterogeneity whatsoever, basically, well, the strategies are very similar, and which makes sense. But when we start increasing the heterogeneity, we see that, again, sampling according to some criterion, which is not just a simple multinomial distribution, improves in terms of convergence and also decrease the variability overall. So this is another empirical demonstration that these schemes actually, it starts becoming useful, especially in presence of heterogeneity.
Thank you.
Yeah. Okay, and yeah, so that's, but of course, the point is that, well, this is where we are now. So testing and application of this kind of approaches is something which is ongoing work, and it's quite recent paper. But what this work shows is that so we define this new way to select clients. So it has nice theoretical guarantees for different things that we would like to have always in federated learning, which is convergence and representativity and variability, variance over iterations. And it's simple, it doesn't change anything of the original federated learning paradigm. So it means that it can be adopted very easily because we just change the way we pick clients, but all the rest, all the structure of federated learning stays the same. And of course, well, which similarity, which clustering method, which way of defining distribution is all open question. We don't have a necessary sufficient condition or optimal condition. We cannot guarantee that. We can just provide some bounds, right? So it's up to us to find the proper way of doing things. And how this applies to more complex and more interesting data sets and more challenging, well, this is all open investigation. So yeah. So more work to do. So this is the first thing I wanted to share with you. I don't know how much time do I have, if there is still time left to tell me.
It's as you wish. It's, I don't know what you have now. Maybe we can do one round of questions.
Okay.
And I see that, or what you want to show, is it related to this?
Not really this. It's still federated learning and variability, but it's not the same approach and not the same.
Okay, so maybe should we do another round of questions and then see at the end of that? Is that okay?
Yeah, that's good.
Are there any questions in the group?
I have another question. So basically, this is a method for getting diverse clients in each iteration, right?
Yeah.
And do you think there are relations to batch sampling? So if I'm just working in normal supervised learning, and I would want my batches to contain diverse images in each step, or in active learning, where I guess the problem is to ask someone to annotate some images, but then we would like them to annotate images that are diverse, so they have less redundancy. So is there, are there links to this work, to those literatures? Or?
That's a very good question. This is a very good point. I never thought about that, but well, the idea of not picking, like not sampling from a uniform distribution, the representative, but trying to find some smart way of picking only the most interesting cases for annotation or like even for training. I believe that there might be something around that. I heard this kind of this problem before, but I'm not aware of any paper specific in the moment. But I believe, yeah, absolutely, this is very interesting. And this idea of course, in this case, we are not interested about convergence, or we change a little bit the criterion that we would like to enforce to this. But this idea of, for example, defining a way to have a similarity or defining a proper similarity between labels or between samples, and then defining a distribution that takes into account of this similarity in the same way we do here. I think this is a very good idea. I would be happy to see something on that.
Thank you for the very nice talk, Marco. I have another question. Like at the moment we looked at, normally the number of clients was fixed, right? How does this change if the number of clients changes dynamically?
Yeah, that's another good question. And this happens a lot in federated learning application, which are maybe not imaging related, because thinking that an hospital drops a study, it's maybe not that likely. But if we think about mobile phones or IoT, we can have devices that just shut down, or they are disconnected, they just go away, and how the dynamically this change. So this is quite challenging, and because even the underlying distribution is something that varies over time. So it's not even stationary. We just not have the problem of heterogeneity, so non-iid between clients, but we have also a base distributions of the data that changes over time. And yeah, this is one of the open questions. It goes well beyond also this problem that we are that I presented. This is one of the big challenges in federated learning as well. This data distribution drift that we have.
Thank you, Mark.
Can I suggest something? One interesting plot to make might be the energy consumption of the benchmark approach and your approach.
Yeah.
Actually, that might be a good selling point.
Absolutely, absolutely. Yeah, computation time and energy consumption, and yeah, that's a good point. That's a good point. The idea is to be more efficient overall, and not having everyone busy in updating things. Also because you're aware, like in mobile phones, you don't want to have your phone all the time training a neural network. Yeah. And even hospitals, you don't want to keep the server busy with just back propagations and so on.
I mean, I guess we discussed at one point about CO2 consumption, and that papers from Google and Facebook should have actually that in there. So this actually might be a good point.
Yeah, absolutely. Yeah. Okay. So, but I don't know, it was 1 hour, right? I don't know how much time we have left. I don't really want to keep all your time. So you could even stop here if you want, or I can go on for hours. So just let me know.
I think everyone should say, now I'm curious about the next part.
Okay.
But do you think you can do a 10-minute summary?
Okay, I can. The next part maybe is more is closer to topics that we address in medical imaging. It will be something we will present at IPME this year, and it's this idea again of heterogeneity, but from a different point of view. We can have different centers. Different centers can have different modalities, so different imaging modalities. Some of them can have clinical information, some of them might not. So there is this sort of heterogeneity. This is not the same heterogeneity we were talking in the other work. And so is a non-iid, but missing not at random. So it becomes complicated to deal, even training a model, because we don't have this general model. And so the idea is that we can still imagine this server-client paradigm, and we can imagine that we want to model basically a global distribution of all this data, and with their own particularities, so with their own specific variation that are center specific. And the idea is why not using a hierarchical model in which we can imagine that the ideal supermodel is something which is global, and then we can sample from this global distribution of parameters to have actually local distribution parameters, and then we can use those local model to generate our data. So basically, we have this hierarchical definition of our generative process. And what we want to do is to solve the inverse problem. Given the data, assuming this hierarchy, we want to infer all the parameters. And it becomes a classical model of variability style probabilistic PCA, where every center, the data varies. So per center, we have samples and we have views. So the view can be imaging, MRI, imaging, PET, clinical, and we assume that given the parameters, the generative parameters, the data is generated by some sort of latent representation, as in PCA. So once we know this latent representation, which is common to every view, we have transformation from the latent space to each view data space that maps the latent to the data. And we assume that everything is linear because it's nice, and we can actually borrow the entire machinery of probabilistic PCA. But we extend this, assuming that this is what happens at the client side, but this parameter, the generative parameters, so transformation, noise, offset, and so on, they are issued by an hyperparameter distribution, which is controlled by the server. So with our own proper assumption on the hyperprior. And we have to estimate everything, the latent, the model parameter, and also, well, tune everything to respect our hyperprior condition. So this is the generative model, the DAG. And as in probabilistic PCA, we use expectation maximization. So at the client side, we have the E step. So we define the latent given the observation, which are Gaussian, if we have our Gaussian assumptions, which are the classical one of PPCA. And then we can do the M step, which is optimizing the expectation of the log joint, as we do in expectation maximization, but under the constraint of the prior. So it's a sort of regularized optimization where the local parameter at the client level are optimized to fit the data, but at the same time to be not too far from the hyperprior at the server level. And once we have optimized everything, we can send all the parameters to the server and to refine actually the hyperpriors to account for all this global variability of the parameters. So we have this estimation also of the variability of the problem across all the clients. And that's it, that's the idea. So some example here, we used ADNI, we had controls and Alzheimer's subjects. We have these different views, so we didn't use very large dimensions. And we generated non-iid distribution, so some centers have only Alzheimer's, some have only controls. There are missing views, not all the centers have every modality. And so this is actually a latent representation of the server side, so how the different clients, the latent space is distributed. So we can model actually these variations between clients with this framework. And here we see actually in the reconstruction how we can reconstruct the data points for the different centers. And we can even, now since we have a generative model, we can impute also missing views. So here we can see actually the distribution of the imputation with respect to the ground truth that was not given. And so centers can benefit from this because they can also impute according to what we see in all the other data centers. We can impute the modality that they don't have. So this is also a nice feature. And in general, in terms of reconstruction, we do well, better than Fed averaging with variation autoencoder or other sort of approaches. Yeah, that's the idea. Well,
so can I ask, the equations look very much like mixed effect modeling.
Yeah.
What is the relationship there? Or is there a relationship?
So in mixed effect modeling, we assume that there is a fixed effect and then there are shifts, which are center specific, and the shifts have a common Gaussian distribution. Here, what we are doing, we are assuming that these parameters themselves are samples from a common prior. And so in that sense, yes, what we are doing is a sort of random effect model, but there is not fixed effect here because all the effects are random because are center specific. And is yeah, well, we have the noise, also we have other parameters other than the scaling parameter or just the coefficient of the linear model. But it's the same idea. You have a hierarchical model like would be a random effect model. Yeah.
But applied over a PCA instead of a regression.
Exactly. So the point that this is something we want to infer in a probabilistic sense. We want a distribution of this.
Yeah.
Yeah, exactly. So that's the principle. And if I'm given 30 seconds more, it's just about showing this, well, this I call it from theory to practice, the talk, because we are working a lot on the practical implementation. So all of what you've seen now is, and most of the papers of the learning are about, well, artificial partition of data, but everything is made in a lab. So there are no centers, everything is virtual, it's a fiction. So how to actually make this like a real? So we are working quite a lot at Inria with a dedicated pool of engineers to develop a library, a software framework for actually deploying federated learning in real setup. So with hospitals, with compatibility with constraints, security, VPNs, and so on. And so this is what this Fed Biomed project is about. That started with the work of Santiago, with another student working with me. But basically, it's really very much about software conception, development, and design. So this, we have an architecture, server, nodes, communication protocols, and so on. So we have VPNs for the network part. We are designing user interfaces because on the hospital, they don't need to waste time in well, working with commands lines and so on. Plus defining how to deploy a model. So using a proper wrapper to define a class of a data set with all these methods for training, for batch. And deploying a network as defined, for example, in PyTorch easily. So wrapper and for the optimization protocol. So how do we want to pass the parameter for batch size and number of rounds and so on. And so you can find all the code is open source, is online. This is an experiment we run already with partners around the world. So we have someone in the US, in the UK, and we were in France, and here just to show that where we use brain imaging data. It was a bit of ADNI, Oasis, human computer project. Everyone had his own piece of data set. And things went well by using this framework. So it was all done in the real setup. So real, federated over the internet, and things were converging. At the end, we obtained this was a variation autoencoder, latent space that was able to sort of even discriminate dementia from controls, which was very, very nice to see. Although the data there was a little bit of everything. So it was brain data in general, healthy, young. And so just to show that this as a proof of concept we presented last year makes sense and works. So more to come. There are quite few people working in this project. So there is an entire development team here in Sophia Antipolis, plus me and well, the students that I showed you presented their work. So hopefully more to come. And we are actually collaborating, of course, with hospitals to having a real deployment of this entire system. So that's where we are very much engaged these days. So that's everything.
Thank you very much, Marco. That was a fantastic talk. Are there any questions still?
Thank you.
Okay, I see there are no questions. Thank you again. And yeah, I hope to see you in person.
I really hope so. Very soon, either here, there, or somewhere.
This was my proper introduction to federated learning. So thank you.
Ah, cool. Oh, wow, that's a responsibility. Okay, well, I hope everything was clear. And in case, well, anything else you would like to discuss, just let me know. And I'll be very happy to get in touch.
Thank you so much.
Thanks again for your invitation. Thanks to everyone.
Bye-bye.
Thank you.
Have a good day.